Start. Hi, everybody. I'm Valay. I am a contributor to Metaflow, and I work at Outer Bounds, where we offer like a managed Metaflow-based solution. Now, my talk, actually all the words written in the title over here are something that I looked up online, and I could not find anywhere else that these words are used together. And what I wanted to say is that to actually explain why this is important, why multiplayer machine learning is important, it is important for me to explain why is it suddenly become so important and what makes it challenging. And once I give that bit of a premise, I can dive deeper into what is Metaflow and how it will help in solving such multiplayer machine learning problems, while also at the end showing a tiny demo on how you could do it practically. So why is it suddenly so important? Now, one cool thing that has happened over the past decade is that machine learning has really, really grown fast. And what it means is that just 10 years ago, we were barely able to identify cats. And now you have chatbots that are talking to you like real humans. And actually it seems a bit dystopian, but even people creating images that are semi-real. You would not be able to distinguish if it's a fake or not, right? And this entire wave of ML progress in research has also trickled down in towards the public, where over the past 10 years, the amount of interest that the public has in machine learning has also grown. And likewise, even the money that is getting funneled into machine learning in terms of investments has also grown a lot. Now, the thing is that even though so much money and so much interest is there, it is still a challenging endeavor to actually build machine learning systems. And there are many forms of complexities that come when you actually go build out these systems. Some of these complexities may be on the actual software side, on how you build the software. And some of the complexities are actually on just operating it and building it with other people within your organization. So let's take a look at a few of these. Okay, so first off, the deep learning revolution has shown one thing, which is you can shove tons of data at a model, and it will perform even better and better as you throw more data or you grow the model bigger and bigger. So in general, if you want to solve many of these tough, scalable, tough problems in ML, it requires that you are able to do tons of computation in a reliable, safe way, all right, such that it is it can cost a lot more money to even do that. Additionally, it's when you build ML software, it's actually very different from normal software. Normal software errors out. If you have some weird input that you had never figured how to deal with in your function would just cry and fail. With ML, it's weird because it's you can give an input that your model's never seen before, and it would give an output that you had never thought of handling before. Right, so even handling bugs in general in machine learning is really, really complex and hard. And many times you would not even realize that your model's buggy because you might have trained it on bad data and it just went through. Because for you, you just saw that, oh, the training finished, it's working. Now, the other side of this, which is outside the complexities of just building ML software, is that when you work in an organization or in a team, people generally have some form of integration into their own infrastructure, into their own clouds. And in general, just wrangling around cloud infrastructure is hard. As you can see from this diagram, AWS or any other cloud provider that you go to has this so many services that play with each other that people just get overwhelmed in thinking about, okay, what do I do just to do a simple hello world? And additionally, when you work in an org, the org generally has their own data and their own processes and pipelines around how that data is created, managed, all of that. Now, the thing is that at the end of the day, when you are trying to do machine learning in an org, you have to integrate into that same hose of data that is there. And that can become astonishingly difficult based on the way general organizations even set up their data practices. Additionally, like a lot of ML happens in Python, and Python, in my opinion, is a terrible language with, like, not terrible language, but sorry, it has a terrible dependency management stack, right? And in general, like, if you go through actually, like, and based on like the way Python works with like the operating system, there are like so many dependencies that may not be even in PyPy, or like you'll have to actually download binaries for that. And that becomes like really, really hard as you want to do it. Like, that becomes really, really hard when you try to do it again and again. The other thing is that when people work in an org with like multiple data scientists or machine learning engineers, everybody has their own preferences on how they want to train stuff. So like somebody would come up and say that, oh, I found like the newest, latest, greatest Llama model, and I want to use that. And someone else might say, no, 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 I want to use like the traditional machine learning techniques that were there to solve this problem. So like different people can have different approaches that they would want to take. And it becomes really hard when you want to collaborate and coordinate amongst all these people who want to apply those different techniques, right? And finally, it's like, if generally in an org, people want to do machine learning again and again, and what it means is that if my code ran once, I want it to run again deterministically. That like it should not have like weird dependency issues that if I try to rerun it the second time, my code will behave differently. And like if that actually starts happening, that the code behaves differently based on like you running it again and again, then like it's not reliable. So overall, like reproducibility of experiments is as important, especially when you're working like in a business, in an organizational setting. And when we like bundle all of these problems together, right, it literally becomes like a death by 1,000 cuts, where like solving one individual piece of all of these problems may be relatively simple, but like when you try to solve them all together, it is like really, really hard. And this is where I wanted to introduce the work we have been doing around Metaflow. So Metaflow is an open source software package that is used by data scientists and machine learning engineers to scale and manage the data science and machine learning projects. The way we see Metaflow is that in general, the machine learning, like in general, data scientists or ML engineers care more about the actual modeling bits of their code. Like they actually want to build good models that can work and that like deliver business value, but they actually care less about where it's running, like what kind of infrastructure it's using. But in reality, the need is such that the infrastructure part is really hard and it is super important. And it's like, so that's why it's like this stack is a way we try to explain what Metaflow does. So the idea is that Metaflow tries to abstract away a lot of the intricacies and nuances of the infrastructure around like actual compute, where you store your data, how your data gets stored, all of that, so that the actual data scientists can just focus on the important core logic parts of the machine learning pipeline that they're building. The way Metaflow works is that it integrates into like various services and orchestrators, so that like data scientists don't need to like know the intricacies of all these different systems, while they can just work with this one unified API. Now, I've been showing this stack and like all these figures, so I would rather want to do one thing, that like I would just want to show you guys how, like as a data scientist, you may start from a notebook, and how the entire progression can happen into Metaflow, and then finally move on to like actually showing you guys different patterns in which you can build machine learning pipelines with Metaflow while collaborating with multiple developers, and also reacting like training models on fresh data. So let's start with a simple thing that, OK, you're playing around in a notebook. You've written some code to, OK, you want to train the model. You get some results by testing it. You're seeing it. You see, oh, this is great. This works. So now what do we do? So we move this code from the notebook into like a Metaflow-based flow. So what Metaflow does is that it exposes this flow spec class. And what any developer would do is that they would inherit this flow spec class to define their entire machine learning pipeline. It also exposes a step decorator. So any form of step in your pipeline can be annotated with a step decorator, and then the interdependencies between the steps can be set via self.next within your function. And anything that you now set to self, which is the special Python variable, will be version controlled automatically. So what it means is that if you train a model and the model that you get, that you set to self over here, is now automatically version controlled for you so that you can access it much later on or even in the future. So let me give an example of what I mean by accessing it later. So like, let's say I ran this flow and I got this model as the output, or like I set the model into self over here. Now I can actually access that same model object later in the future whenever I want to and do whatever I want with it. So like once it has been version controlled, every time you execute Metaflow, once it has been version controlled, when you execute Metaflow, as you see over here, when I say python myflow.py run, you can access it via the Metaflow client API. Oh, sorry. That you see over here, where the run is like an object that we expose, which explains the instantiation of a flow. And what I mean by instantiation is that when you're actually executing it, the final outputs can be accessed through this run object or this flow object. And so every time, one more key thing is that every time you execute, it's like you're minting a new run ID, which is like an identifier for your execution. So like everything is then namespaced on all the artifacts that are created are namespaced under just that run ID or of that execution. So now that we have a flow that is working on my local machine, I want to make it reliant enough that I can reproduce it again and again. So one way I can do it is by just freezing dependencies. So Metaflow exposes these conda and PyPy-based decorators that hook into like conda and PyPy package repositories. And you can like just slap one of these decorators on the flow and set whatever libraries and versions that you need for those libraries. And all of those code packages will automatically get stored and be used when you're actually executing all these steps. So if the train model function is using scikit-learn underneath, then it will actually just use 1.1.2 version of scikit-learn when the train model function is running. Now that we've frozen dependencies and we have like a good idea of like our flow is running properly and we are able to like get our results on our laptops, now what I want to do is I want to actually throw more beefy compute at it. Okay, like I want to scale it up, throw tons of memory, even a few GPUs if I can. And this is where like I think the real magic of Metaflow starts to appear. So Metaflow integrates into these various compute mediums like Kubernetes, AWS Batch. And for simplicity's sake, the way I would want to explain Kubernetes for this talk's context is that imagine it's just this giant cluster of servers that is seen as this one unit. So like if you are trying to like deploy something where you need specific amounts of memory, CPU, whatever, you can just tell Kubernetes that, OK, I have this definition of a job. I want to deploy it, and I want so-and-so CPU and memory. And Kubernetes will figure out in where to place that job within the entire cluster. So the way Metaflow works with Kubernetes is that when a user is running a flow, by calling myflow.py run, we actually save all the code that you have written on that is going to run on some artifacts like in some data store like AWS S3, GCS, whichever cloud provider you're hooked into. And then it'll actually launch jobs on Kubernetes while using the same code that got stored earlier. So giving an example, now that I want to scale out, I can just slap this Kubernetes decorator, and I can say how much memory I want, or how much CPU, or how many GPUs I want. And automatically, Metaflow will actually actually run this step, this start step, inside Kubernetes with a job with 64 gigabytes of memory, which is pretty cool. Now that I've scaled out and I know that I am able to run my code on a remote setup, I want to make it run autonomously. That I want my code to run regularly on some cadence where I don't have to manually go punch buttons to start it or do stuff with it. So additionally, this is where I want to come to this whole concept of deployments in Metaflow. That once you have done your prototyping and you want to deploy it autonomously, Metaflow integrates into these various schedulers or orchestrators like Argo workflows, Apache Airflow, AWS step functions. And what these orchestrators basically help do is that they will help run your code without you having to manually press buttons to do it. So in this case, for Kubernetes, Metaflow integrates into this tool called Argo workflows. And Argo provides a way that once you deploy this flow onto Argo, all the code would have been persisted before. And when you would have scheduled the flow to execute, Argo will automatically execute that flow. And everything in Metaflow that I just spoke about earlier, like your dependency management, your versioning, your compute specification, all of that would be working in tandem with your deployment. So and then the way I can do these deployments is that it exposes more decorators. So you have a schedule decorator, for example. So when you run this command, myflow.py argo workflows create, it will actually schedule this workflow on Argo where, for example, the start step will run with 64 gigabytes of memory. And it will run daily on its own because now your dependencies are frozen. So you can basically get a deterministic way that your code will run without having any failures. Now, deployment has many fascinating patterns because people would want that, OK, I want to run something daily or weekly. But sometimes you want to react to different kinds of events that are happening so that based on that, you would want to trigger some form of training or do something. So Metaflow exposes this notion of events where, let's say, you have new data that is available. You emit an event. The event gets caught by Argo. It triggers the training flow. The training flow created some model artifacts. It raises another event that triggers an inference flow. And then the inference is done. And the same inference flow is going to use whatever model that got created in the training flow. So, and the way we actually expose the events on the Metaflow side is using these decorators called trigger on or trigger on finish. Now, what does trigger on do is that it will subscribe this Metaflow flow to this data.prep event, for example. And what that means is that you go and say that, OK, myflow.py argo workflows create. It deployed this in Argo workflows, and it told Argo that, OK, when you get the data.prep event is when you need to start executing this flow right here. And additionally, what we've also done is that you can actually stitch together different entire flows instead of even just listening to individual events. So for example, this data prep flow that you see over here was an upstream flow that finishes, that will raise an event that I, as data prep flow, have finished. you can start executing now the train model flow. So like you can actually stitch together separate flows that you write in Metaflow, and they can all be stitched together through this whole eventing mechanism where they'll all execute asynchronously once individual flows complete, finish execution. Now that we've talked about events and like deployment patterns and everything, I think like I want to now come to the core crux of this talk, which is around multiplayer machine learning and like how to like collaboratively build all these models. Now, one key aspect to think about, especially with regards to multiplayer machine learning, is that whoever is doing any form of deployment, you don't want to step on your coworker's shoes. And what it means is that like if I go build some model, I don't want that if my coworkers also build something that I actually like, his work gets invalidated or like his executions get like stepped on and like my executions take over his execution. So like we want a way where all of us can like, me and all my coworkers can like deploy stuff without it interfering with each other. And so like the ideal scenario would be like if Alice tries to deploy something, then Alice gets a separate execution. And if Bob tries to deploy something, Bob also gets an entirely separate execution where both of them are trying to execute the same flow, but they are going to get separate instances that need to get executed. And this is where there is this concept in Metaflow called projects, that you can add a project decorator to this flow. And anytime any user now starts executing something, or like anytime a user tries to like run something or deploy something, it will be namespaced under that user. So that means that if I, as Valay, try to execute this flow, whatever objects that are created as a part of this flow will be namespaced under me. So if Alice executes this flow, she can actually write, as you see over here, an Alice model, right? Where Alice may have her own special model that she's building and she's testing on. So if Alice and Bob both are executing this flow, Alice and Bob will both have separate execution instances. They will have completely separate data artifacts that get created as a part of this flow. So giving an example, this was Alice executing. Now this is Bob executing. And as you see, like these bold arrows are trying to show what effect do these different decorators have on the entire stack. So for example, Bob's model will be versioned separately from Alice's model. And like even the deployment that Bob will do will be completely separate from Alice's deployment. And yeah, as I explained, like it will even work for deployments where you can put the schedule. You can even hook it up to like events separately. So like I have this data prep event over here. I can Bob's actual deployment will be hooked up to the data prep event. And so if Alice wants a separate event to like be hooked up, she can literally write a separate event name over here and it'll just be hooked up to that event and it'll not step over Bob's work. So additionally, Metaflow has this concept of branches in a project. So like if people want to do one-off executions to like test stuff, they can like actually create like a branch. And what I mean by a branch is that on the command line, you just provide an additional argument saying that this is my new branch that I want to test on. And boom, it'll like run a separate execution. Everything will be namespaced under that branch. 1 second. Yes. So now comes like the real meat of the talk, which is like how do you train on fresh data? And basically, how do you do this reactive form of machine learning? And based on all of the things that I just said earlier, one key thing, like the smallest explanation I want to give here is that if you want to train on fresh data constantly, events are an excellent mechanism to help enable you to do that. where anytime new data is created, you can just raise an event, and then the event can get caught by Argo in Metaflow, and everything will start working on its own. Additionally, if multiple people are trying to train models on fresh data, the project decorator that I just talked about earlier is an excellent means to namespace all your events, your deployments, and the data artifacts created from that. So let's go through some use cases, okay, where I had two major use cases in mind where users are actually controlling the data that they are using for their models versus a use case where users have no control of that data. Data is prepared by completely someone else. They just want to actually train on whatever they're getting. So let's take the first one where users are not managing any form of data creation. So the simplest thing to do in this form of scenario is that both Alice and Bob will listen to the same event. And when that event is raised, both Alice and Bob's machine learning pipelines will start getting executed. So giving an example, this is Alice's model where she has set trigger on to the data prep event. And in the same way, this is Bob's model and Bob's flow where they have he set a subscription on the data prep event. And as you will see, both of these flows, once they are deployed on Kubernetes and Argo, they will run as separate instances when that event is raised. Now, let's take the second case of where users want to manage their own data. They want to make their own data. They want to set up everything on their own. And they even want to raise their own events, right? And this is where the whole idea of projects and namespaces really, really shines. Because the really cool thing with Metaflow is that if Alice has some flow which is raising an event on its completion, that event itself is namespaced to Alice's work. So what that means is that that event will only be caught by any flow that has been any flow that has been deployed by Alice and no one else. So the good bit about that is that if I'm experimenting with multiple event, if I'm experimenting over multiple flows that I'm stitching together via events, and other people are also working on those flows, with projects and namespaces, you can actually not step on each other's shoes, and there will be complete separate events. So everybody can experiment however they wish to. So an example over here is that let's say that there's this data prep flow, which is scheduled on a daily basis. It has a project decorator, and at the end, it just creates a data set and it validates it. Now, when the flow finishes execution on Argo, it will raise an event saying that I am done as the data prep flow. And the event, since it is namespaced, where right now I'm user Bob. So one second. Yes. So since the event is namespaced, when you put the trigger on finish decorator on this flow, and you say that, OK, I am listening to the data prep flow, then only the execution of Bob's data prep flow raising the event will actually trigger the train model flow written by Bob. So if Alice has written a separate flow like this, like the train model flow, then Alice's execution won't start. Only Bob's execution will start because all the events have been namespaced. Actually, yes, now that I've given everybody a rundown of how these things can work, how different use cases around managing or training on fresh data can be handled, I want to just dive into this tiny demo example that we've curated. So the idea was that, OK, I'm working in an org. There's a team of people who are creating data sets. And actually, the demo is going to be about the first use case. And it's actually not that hard to even port it to the second use case. But in this demo, the idea is that I am there's somebody who's creating the data. And when they create the data, at the end, they're raising an Argo event. Over here, one key nuance is that I didn't want to actually take data from places, so I'm just like piggybacking off Hugging Face Hub. But this is just a demo. Now, once the data has been created, I want to actually start training some like llama model on this new data, and that's majorly it. So how do we do that? Like, you raise an event that is the main connective tissue between these two flows. So let me get into it. Second, yes. Okay, perfect. So let's say my terminals, as you see, there's an Alice, there's a Bob, and this is a data prep. So let me just set up some data prep first. So as you see, I will first deploy the data prep onto Argo. And as you see, it is bootstrapping virtual environment, and now it has been deployed. I will trigger it so that in just a bit, just to show you guys how like the execution will turn out. Now, I'll go to Bob's flow, and so all of this code is open source, by the way. It will be in the slides if you guys are interested. So perfect. So I'll do, as you see, remote flow, Argo workflows create. And as you see, it is saying this is the first time I'm deploying as Bob. And it has now created like a separate instance on Argo for Bob. Now I'll do the same thing for Alice. So now it's doing the same thing for Alice, where as it is saying that the workflow will automatically trigger when there's this event that gets raised, which is the alpaca.dataprep event. So now both of my flows have been wired up on Argo. I can now actually trigger their execution via raising this event. So this data prep flow will now raise an event, and based on that, we will see the execution of the other two flows starting too. Now, the other cool bit with Metaflow is that it exposes this user interface called the Metaflow UI, where you can actually see and track all the executions that are happening. 1 second. Yes. So perfect, yeah. So in the past, I had trained some of these flows before. So as you can see, this is how it turns out. Like, you can actually go inspect. You can actually see all the logs that have been created as a part of your execution. And additionally, Metaflow has this nifty little feature called cards, which inspires from this model cards concept that came around when machine learning has grown. So as you see, this is like an entire description of what happened in the flow, what kind of parameters did it have, any kind of artifacts that got created as a part of it. And 1 second. So as you see, this data prep flow has started, and it is executing. And once this will finish, it will raise an event that will trigger the execution of this llama instruction tuning flow. So, and you can see, as you see over here, anytime anytime a flow gets instantiated from a separate event, you will get to see the event on the Metaflow UI. And as you see, yeah, over here, Bob's flow started execution, and so will Alice's in just a bit. There's not enough compute capacity. I'm like throwing too many GPUs at this. And to conclude, Metaflow offers this way where it holistically tries to integrate into the entire machine learning infrastructure stack so that data scientists and machine learning engineers don't have to worry about like the intricate nuances of the low-level stuff, and they can actually focus on building their models and the higher level stuff. And thank you. And if you guys want to use Metaflow for free, we have a sandbox environment that has all of this set up for you. You don't have to do anything. You just have to visit the sandbox and play around. But yeah, thank you so much. And